So in this problem, we're asked to use the method of sections to determine forces in member CD and member BD. And we're also going to check stability, or not stability, determinacy of this truss. So our first step would be to draw the global free body diagram. Of the truss, and here we'll identify all of our forces, including our reactions, and have something that we're ready to use as our free body diagram for analysis sake. So for this truss we have a pin connection and a roller connection. That means that at joint A we have two forces, RAY and RAX. And then at joint F we have a single force, RFY. And that force is perpendicular to the surface. So the surface is running horizontally, so the first force is vertical. Applied to this truss, we have some external loads. We have 150 kilonewtons down and 100 kilonewtons to the right. We know some dimensions. We have 5 meters, 4 meters, 5 meters. This angle happens to be 45 degrees. That means to me that this height is also 5 meters. If we, lastly, we're going to label our joints here, A through F. And we can begin to assess our determinacy. So if we remember, the equation for determinate check is degree of static indeterminacy. SI is equal to B plus R minus 2J, where B is equal to the number of members, which we can count here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So a member spans between two joints. We see that this has a continuous straight line, but there are joints intersecting it. So we count this member as 1 member, 2 member, 3 member. The number of reactions, well, we've already identified that as 1, 2, 3. And last we'll get the number of joints. 1, 2, 3, 4, 5, 6. Now, the location of our supports also counts as a joint, as we saw here. So occasionally people will make the mistake of not counting joint F and joint A as joints. They are joints for the sake of this calculation. Once we have this, we can plug that into our SI equation. And we see that we have 9 plus 3 minus 2 times 6. So SI is equal to 9 plus 3 minus 12 is equal to 0. Therefore, if SI is 0, the degree of static indeterminacy is 0, we can say we have a determinate truss. And if the truss is determinate, it means to us that we can solve for all of the member forces and all of the reactions using only our principles of equilibrium. So now we are asked to find forces we've accomplished A here, so just put a little A. We finished A, and now we're looking for the force in CD and the force in BD. And if we're using method of sections, we have to pass a cut through somewhere in this truss. And I have chosen to pass a cut AA, to cut through AA here, because it exposes both of those members, and I know since I'm only cutting through 3 members, I'm exposing 3 unknowns, and I have 3 equations of equilibrium. So as long as I can solve for these reactions before I make that cut, I can now put either of those cut sections into equilibrium, and I can definitely solve for all of these member forces with the equations that I have. As I mentioned, we often have truss members, well, we always have truss members meeting at a joint, and that means sometimes a lot of the forces meet at the same joint. And this allows us to take sum of moments about that joint itself and eliminate a lot of the forces in our calculations. So just because I only cut through 3 members here doesn't mean we couldn't solve for some of these member forces if we cut through 4 or 5 members as well. We just have to be creative with how we cut. However, since I only cut through 3, I am 100% positive that I can solve for the forces in this cut. So at this point, let's go ahead and find our reaction forces. So let's find the RFY force. So if we're doing a section cut, we're only going to be looking at one side of that truss. And the whole goal of the method of sections is to solve this truss with the minimal amount of work. So here I'm only going to find one of the reactions. And to do that, we will take sum of moments about point A and set that equal to 0. And let's briefly look at our truss again while we do this calculation. I don't have room to put the free body diagram there, so we'll take this one here. Recall that we have a vertical force at F here and our 2 reactions here. If I take sum of moments about A, I'm only using the one unknown in that equation. And this equation is written as E, or RFY, sorry, not E, times the distance between A and Fy, which is 5 plus 5 plus 4 meters, is 14 meters, minus 100 times 5 minus 150 times 9, and that's equal to 0. So if we calculate out the value of RFY here, we get RFY happens to equal 132.143 kilonewtons. That's a positive value, so that indicates we drew it correctly. It's acting upwards. Now, let's follow through with our cut at AA, and we're going to be answering part B here. So let's draw our free body diagram of that cut at AA. So here we'll cut at AA. And that free body diagram should show us our member forces at the location of that cut. So here we have we have an external load of 150 kilonewtons at the top joint there, and we have solved for values of our Fy of 132.143 kilonewtons. Now, we don't know 3 quantities on this diagram. We don't know F dB, we don't know F DC, and we also don't know F EC. Of those three, we're only looking for two, FDC and FDB. And we can label some joints while we're at it. We have joint E, joint F, D, and over here we have joint C that we'll use later. Distances on this diagram, we have 5 meters, 4 meters to the location of joint C, and a height of 5 meters. So if we're interested in FDC first, we have a couple of options. We could try and take sum of moments about a point. That would allow us to directly solve for FDC, but there's no particular point here where we could eliminate FEC and FDB from that calculation right away. Since these are parallel to each other and they don't intersect at the same point, we can't find one point to take sum of moments about that will eliminate both of those forces from our calculations. Instead, we should probably take sum of forces in the y direction and calculate the y component of FDC directly. Because there's no y component of FEC or FDB, we can solve for FDC with one equation. Before we do that, let's look at our components of our force FDC. If this is FDC, then we can say we have a component FDCY and a component FDCX. And we could say that this triangle is proportional to a triangle comprised of a distance, a y component, and an x component. And this triangle is 4 meters, 5 meters, and the length there. So we have 5, 4, and we have the square root of 4 squared plus 5 squared, which happens to equal 41, root 41 on the length. So from that, we can say that we now have a relationship where FDC over root 41, so the force divided by the length, is proportional or equal to FDCY over 5. Therefore, we can now write an equation for FDCY, or FDC in terms of FDCY, and we can say that FDCY is equal to 5 over root 41 FDC. So we simply multiply that 5 over root 41 to the other side. And FDC is equal to root 41 over 5 FDCY. So we have the relationship between the vertical and the horizontal, or the vertical and the magnitude of the force itself in its actual direction. Now we have the ability here to take the sum of forces in y and set that equal to 0. And we know that this FDC really is a sum of its force components FDCY and FDCX. So if we add up all the forces in the y direction, we end up with our Fy acting positive minus 150 kilonewtons, the applied force at joint D, minus FDCY is equal to 0. Now FDCY we've drawn as going down, and that's because we drew FDC as a tension force on the member, and we draw the components such that they will add with vector summation to equal the actual applied force vector. So since it's going down, we put it in our equation as a negative number. And then whatever it comes out with, if it's positive, it means we drew it correctly. If it's negative, it means we drew it backwards. If we put in the values for this, we have 132.143 minus 150 minus FDCY is equal to 0. And this gives us FDCY is equal to minus 17.857 kilonewtons. So the negative sign there indicates that we drew it backwards. But before we change any of our drawing, let's calculate FDC. So since we have FDCY, we can say FDC is equal to the root of 41 over 5 FDCY from what we calculated based on similar triangles. And this is equal to root 41 over 5 onto minus 17.857. So we can say FDC is equal to negative 22.868 kilonewtons. In other words, FDC is equal to 22.868 kilonewtons in compression. Since it came out as a negative value, it means it's in compression following the sign convention that we established in the course. So at this point we're done problem B. We found the force in FDC. So we can move on to the next problem, problem C. And before we do that, let's just investigate the drawing we have here and determine how we're going to approach finding FDB. We found FDC, so we can find the component FDCX if we wish, but we still don't know FEC. That means if we take sum of forces in X and set that equal to 0, we will have an unknown FEC and an unknown FDB, and we can't solve it directly. We already took sum of forces in Y, and it gave us nothing in relation to these values because there's no Y component of those forces. This indicates that our only option is sum of moments about a point. Excuse me. Now we have several points that we could choose. We would like to pick a point where FEC is eliminated from the equation. That means that we want to pick that point somewhere on the line of that force. And the reason for that is because we don't know the value of FEC. Since we know FDC, it doesn't matter where on that line we pick it, because we can always put the force components of FDC in our equation. That being said, if our forces come through point C, both FEC and FDC, they're both eliminated from our calculation. And this has two benefits. One, we don't have to worry about finding force components and finding distances of FDC, FDCY, and FDCX. And two, if we made a mistake in this calculation, it won't impact the calculation of FDB. So we will take sum of force or sum of moments about point C to find FDB. So we'll use the same cut to do this. So we'll use cut AA to do this. And we'll use the same free body diagram as we had before. So we'll use the free body diagram from part B to solve this, just to save a step in our drawings. So now we're going to be wanted to solve for the sum of moments about location C and set that equal to 0. Let's just pull that free body diagram back up again and repeat one point. We are working in the XY plane here, and any point on this paper or off the paper anywhere is in this XY plane. We can take sum of moments about that point, and it has to add to 0. That's the equilibrium in the XY plane, about the Z axis in any point in the XY plane. That means we don't physically need to be on some location in our truss or in our section. So here we're taking moments about a point that's outside of our section, but the moment equilibrium is still a perfectly valid equation. So we're going to need for that the force dB, its moment arm, force RFY, its moment arm, and the 150 kilonewton and its moment arm. And they will all add into our equation using our plus or minus according to their direction. So we will first add in RFY times 9 meters, and we could say RFY is going to be resulting in positive rotation. To that we will add plus FdB times its moment arm, which is 5 meters, and that's also positive. And we will subtract from that 150 times its moment arm, which is 4 meters, and that's rotating it negative, and that's set equal to 0. And if we plug in the values for that, we know the value of RFY is 132.143 times 9 plus FdB times 5 minus 150 times 4. And I made a mistake in my previous calculation here, so I'll have to do that right now. It'll just take a moment. So we end up calculating FdB is equal to minus 117.857 kilonewtons. Since it came out as negative, and in our free body diagram here we had drawn it as tension positive, and it came out as negative, that means it's going the opposite direction. That means that FdB is equal to 117.857 kilonewtons in compression. So at this point we've found everything we've been asked to find for this problem, and we can move on to finding or to drawing our summary diagram. And our summary diagram won't be complete since we don't have all the quantities here. We have our reaction force of 132.143 at Fy. We have our member force in CD that we calculated, which is compression, so we'll draw some compression arrows on it, and we'll write the member force directly on the member of 22.868 kilonewtons in compression. And then at the top, dB or BD, we also found a compression force. So we'll draw our compression arrows, and we have 117.857 kilonewtons in compression. And at that point we finished our summary diagram for the problem in question. And we'll note that this method was very efficient for us because we didn't have to solve for member forces in 1, 2, 3, 4, 5, 6 of the members of the truss. And we didn't even need the reactions at A. So there was plenty of stuff left over in this truss that we didn't bother including in this particular example.